Vapor refrigeration cycle. What cycle do actual refrigerators use? Let us recall a two-phase Carnot refrigerator. This transfers heat from a low-temperature heat source, which is at Tc, to a high-temperature heat sink, which is at Th. We have an evaporator whose pressure is equal to the saturation pressure at Tc. We transfer heat from the heat source to the fluid in the evaporator. The fluid goes into a compressor to which we provide work. The fluid then comes out of the compressor at a higher pressure, which is equal to the saturation pressure at Th. The fluid loses heat in the condenser to the heat sink, and it comes out at saturated liquid. This is then expanded isentropically in a turbine back to the evaporator pressure. Now there are two problems with this. One is that the fluid which goes through the compressor from 4 to 3 is a two-phase mixture. Having a two-phase mixture going through a compressor can lead to serious damage on the compressor blades. The other problem is that the amount of work which is done in the turbine is very small. It's usually not worth the trouble and the expense of installing a turbine to recover this small amount of work. We therefore modify the reverse Rankine cycle. Instead of heating the fluid from 1 to 2, where point 2 is a two-phase mixture, we heat it up all the way until it becomes a saturated vapor. The fluid which is then going through the compressor is a superheated vapor. This is then our refrigeration cycle. From 1 to 2, a liquid vapor mixture is heated in the evaporator until it becomes saturated vapor. From 2 to 3, the saturated vapor is compressed isentropically in the compressor until it becomes superheated vapor. From 3 to 4, the superheated vapor is cooled at constant pressure in the condenser until it becomes saturated liquid. And finally, the saturated liquid passes through an expansion valve to the lower evaporator pressure. The evaporator coil is placed inside the refrigerator cabinet where it is at the low temperature. The condenser coil is placed on the exterior of the refrigerator, either at the back or underneath the refrigerator, and from here it loses heat to the surrounding air. The expansion valve is a simple device in which fluid flows in at high pressure and it flows out at low pressure. We can do an energy balance on this by treating it as a controlled volume. In the expansion valve, there's no heat transfer, there's no work done, and changes in potential energy and kinetic energy are negligible. The energy balance then simply becomes H1 is equal to H2. The enthalpy of the fluid remains constant as it flows through the expansion valve. The expansion process in the refrigeration cycle then is shown as a dotted line from 4 to 1. We show this as a dotted line because this expansion is a highly irreversible process, and so we cannot represent it as a quasi-static process on a TS diagram. The heat input from the refrigerator interior is supplied to the evaporator. The refrigerator temperature is therefore higher than the temperature of the fluid in the evaporator. In the condenser, we reject heat to the room air. The room temperature, therefore, is lower than that of the fluid in the condenser. We can now do an energy balance on this refrigeration cycle. Heat is removed in the evaporator. The heat per unit mass of fluid, QC, is equal to H2 minus H1. The work done in the compressor per unit mass of fluid is H3 minus H2. The heat lost to the surroundings per unit mass of fluid is H3 minus H4. The flow through the expansion valve is a constant enthalpy process, so H4 is equal to H1. The coefficient of performance of a refrigerator, COPR, is equal to Q dot C, which is the heat removed from the cold space, divided by W dot C, which is the power supplied to the refrigerator. The coefficient of performance, therefore, is given by H2 minus H1 divided by H3 minus H2. An air conditioner works on exactly the same cycle as a refrigerator. In this case, the cold space is the house interior, which is maintained at a lower temperature than the exterior air. But what about the winter, where the house interior is warmer than the exterior air? We can use exactly the same device, the air conditioner, to heat the interior of the house. In this case, we reverse the flow through the air conditioner. The condenser now acts as an evaporator, and it takes heat Q dot C from the exterior. The evaporator now serves as a condenser, and it rejects heat Q dot H to the house interior. The compressor and the expansion valve are exactly the same, except that the flow is now reversed through them. This device is a heat pump. The advantage of using a heat pump is that it is more efficient than an electrical heater. If we were using an electrical heater and we were simply taking the power, W dot C, and putting it through a resistor, then the heat supplied Q dot H would be equal to W dot C. In a heat pump, the heat which is supplied is equal to W dot C plus Q dot C, which is the heat taken from the cold space. The performance of a heat pump is measured by the coefficient of performance. The coefficient of performance is defined as Q dot H divided by W dot C. Substituting the terms that we had got from our energy balance, the coefficient of performance is given by H3 minus H4 divided by H3 minus H2. A heat pump can be used for cooling in the summer and heating in the winter. The advantage is that it replaces separate air conditioner and heater units. This is a cost-effective solution if the exterior temperature in the winter is not too low. In places where the winters are really severe, the coefficient of performance of the heat pump is usually too low for it to be cost-effective. To summarize, the reverse Rankine cycle is used for refrigerators. The refrigerant is evaporated at low temperature and pressure and condensed at high temperature and pressure. Air conditioners work on the same principle as a refrigerator, and an air conditioner can be reversed to operate as a heat pump.